Hello students, continuing with curve sketching using calculus, we will consider a rational function to graph. The general form of a rational function h of x is of the form f of x divided by g of x, where f and g are polynomials and g is not equal to 0. Shown on our screen are a few examples of rational function graphs. Let's start with an example and graph our masterpiece. This is the rational function we would like to graph. H of x is equal to x minus 4 all over 2 plus x. To do so, we will compute the first 7 steps, collect the data, and graph our masterpiece. We will start with step 1, and step 1 says to find the domain of the function. Since we have a rational function, we want to find where our function is undefined. That is, where our denominator is 0. Because division by 0 is undefined, we want to set the denominator equals to 0, find the value of x that will make our denominator 0, and exclude that value from the real numbers. So our denominator here is 2 plus x, and we set it equal to 0. We want to find x, so we subtract 2 from both sides, and we get x equals to -2. Now the domain will be -∞, -2. As you see, we excluded -2 from our domain, and -2 infinity. We're done with the first step. We now compute the second step that says to find the x and y intercept. I will first start with computing the x intercept. So step 2, the x intercept. To find the x intercept, we want to let y equals to 0. So at y equals to 0, and we know h of x is the same as y, so I want to substitute 0 for h of x and bring x minus 4 over 2 plus x. Now when is this true? This is true if our numerator is 0. It is sufficient to show that the numerator is 0 for this equation to be true, because 0 divided by any non-zero number is 0. So if we set x minus 4 equals to 0, and adding 4 to both sides, we will have x equal to 4. Notice the x-intercept is a point, so I have to represent my answer as a point. So I let y equals to 0, and I found that x is 4. This is the y, this is the x-intercept. I now look for the y-intercept, and the y-intercept happens when x now is 0. So I let x equals to 0, and now I want to evaluate h of 0. So the original function h at x equals to 0 will be 0 minus 4, 2 plus 0. This should give me -4 over 2, and this is going to be -2. Again, the y-intercept is a point, and I want to represent my answer as a point. So I let x to be 0, and I found that y is -2. I'm collecting data so I can use them later to graph. I'm done with step 1 and 2, and I'll move now to step 3. We now arrive to step 3, and step 3 says to find the vertical and horizontal asymptotes. So step 3, we first want to find the vertical asymptote. to find the vertical asymptote, we will set the denominator equals to 0 and solve for x. Our denominator is 2 plus x, and we want to set that equal to 0. To solve for x, we want to subtract 2 from both sides to have x equals to negative 2. And this is our vertical asymptote. To find the horizontal asymptote, we want to find y, the value of y when x approaches a very large positive number or a very large negative number. That is, we want to evaluate the limit of our function as x approaches positive and negative infinity. Since both will give me the same result, I will combine the process. So I want to evaluate the limit of our function x minus 4 all over 2 plus x as x approaches plus and minus infinity. Now, to evaluate the limit of a function at infinity, we want to divide each term of our function with the variable in the denominator that has the largest exponent. In our example, x is the variable with the largest exponent in our denominator, and we want to divide each term in our function by x. So we're going to have limit as x approaches plus or minus infinity, and divide by x each term. We will have x over x minus 4 over x all over 2, and 2 is divided by x plus x divided by x. If you would like to see more examples of limit at infinity, you may look for one of my earlier videos. Now, simplifying the function, we will have the limit as x approaches plus and minus infinity. X divided by x will be 1 minus 4 over x, and in the denominator we will have 2 over x plus 1. What will happen to the terms divided by x when x is approaching a very large positive number or a very large negative number? Our terms, each one of these terms, negative 4 over x and 2 over x, will be approaching 0. And we are left with 1 in the numerator, because the term negative 4 over x will just approach 0. And the term 2 over x will approach 0, and we're left with 1 in the denominator, which is equal to 1. And now y is equal to 1 is our horizontal asymptote. We arrived to step 4, and step 4 says to find local extremes. If there are local extremes, they will happen at the critical points. To find critical points, we will first compute the first derivative of our function. So step 4, we want to find h prime of x. But first, I want to label the function x minus 4 with f of x, and the function 2 plus x with g of x. Because I have a rational function, and I want to apply the quotient rule to find the first derivative of the function. So the quotient rule says to multiply g of x times f prime of x minus g prime of x times f of x all over g of x squared. I like to state the functions that I labeled here and find their derivatives so I can substitute back in h prime of x. I will start with f of x, and that is equal to x minus 4. And I want to find f prime of x, which is using the power rule for derivatives. I will have 1. Negative 4 is a constant. The derivative of a constant is 0. G of x, I let g of x equals to 2 plus x. So I will state that here. And g prime of x is going to be equal to 1. I will substitute these values in h prime of x to have g of x is going to be 2 plus x times f prime of x, which is 1. So I'm going to just have 2 plus x minus g prime of x is 1 times x minus 4, which is just x minus 4, and which is the value of f of x, divided by g of x squared, which is 2 plus x squared. Now simplifying the numerator, we will have h prime of x equals to 6 over 2 plus x squared. Now where does the critical numbers happen? Critical numbers happen when h prime of x is 0 or undefined. If I let h prime of x equals to 0, then I only have to worry about the numerator to be 0, because 0, as I said earlier, divided by any non-zero number will be just 0. But in this case, my numerator is a constant which is not equal to 0, in this case 6, and 6 will never be 0. So h prime of x equals to 0 did not give me critical numbers. I'll have to consider the other case where h prime of x is undefined. H prime of x is undefined when x is equal to negative 2. Notice that x equals to negative 2 is not in the domain of my original function h of x. So I cannot call x equals to negative 2 a critical number. So my conclusion would be no critical numbers. And I'm done with step 4. Step 5. So step 5 says to find intervals where the function is increasing and decreasing. To do so, I will graph the number line for h prime of x, label the point where my h prime of x is undefined, which is x equals to negative 2. So from negative infinity to infinity, I'm going to label negative 2 here. I know at this point the function is undefined, and I want to evaluate, randomly choose values on each interval, negative infinity, negative 2, and negative 2 infinity. Choose random values, evaluate them in h prime of x to see where the slope is positive and where the slope is negative. Notice h prime of x has a positive 6 in the numerator and has a positive value in the denominator. Any x value we will substitute in the denominator, we will always have a positive value because of the square. So because our 2 plus x is raised to the second power, so h prime of x will always be positive. So regardless of what values we choose from each interval, we will always have the slope positive. The conclusion we get from this is the original function h of x is going to always increasing on its domain. And we're done with steps 4 and 5. We now arrive to step 6, and step 6 says to find the inflection points and concavities. To find the inflection points, we want to compute the second derivative of our function. To do so, we will apply the first derivative to h prime of x. To compute the second derivative, we may apply the quotient rule or the chain rule of derivatives. I would like to apply the chain rule of derivatives to find h double prime of x. But first, I want to rewrite h prime of x with a negative exponent. So we are in step 6, and I want to rewrite h prime of x with a negative exponent, which is 6 times 2 plus x raised to the power of negative 2. Now computing h double prime of x, applying the chain rule for derivatives, we will have negative 12 times 2 plus x raised to the power of negative 3. I want to rewrite h double prime of x with a positive exponent, and that will be h double prime of x equals to negative 12 over 2 plus x to the third power. When does the inflection point happen? Inflection points happen when h double prime of x is 0. So I'm going to write the value 0 under h double prime of x and bring this down, which is negative 12 over 2 plus x to the third power. When is this equation true? This equation is true when the numerator is 0. But our numerator is negative 12, and negative 12 will never equal 0. Notice that we still may evaluate values around the value of x that will make h double prime of x undefined. In this case, at x equals to negative 2. So I will draw the number line. And label negative 2 the x value that will make h double prime of x undefined. Then evaluate random x values from each interval in h double prime of x to decide on which interval is h double prime of x positive and negative. I will first consider the interval negative infinity negative 2. So the interval negative infinity negative 2. If I let x be negative 3 in this interval and evaluate h double prime of x at negative 3, I will have negative 12 over 2 minus 3 cubed. 2 minus 3 is negative 1. Cubed will be just negative 1. Negative 12 divided by negative 1 is just 12. Positive 12, which means this interval, I want to label this interval with a positive sign to tell myself not only at x equals to negative 3 I will have a positive slope, but at any value in this interval negative infinity negative 2, if I evaluate the value in h double prime of x, I will have a positive slope. Now I want to consider the interval negative 2 infinity. If I let x be negative 1 in this interval and evaluate h double prime of negative 1, I will have negative 12 over 2 minus 1 cubed. 2 minus 1 is 1, cubed is 1. I will have negative 12 divided by 1, that will be negative 12, which is less than 0. So I want to mark this interval with a negative sign again to tell myself any value in this interval evaluated in h double prime of x will give me a negative slope. Now what does this mean? What information can I have about my original function? What this means that at negative on the interval negative infinity, -2, the original function h of x is concave up. So let's write this down. So h of x is concave up on negative infinity, -2. Also, this negative slope tells me that on this interval, so h of x will be concave down on the interval -2 infinity. And we're done with step 6. We arrive at step 7, and step 7 says to evaluate additional points. We already have the x and y intercepts, but it would be helpful to evaluate few more points to have a better sketch of our graph. Better points would be around the vertical asymptote at x equals to -2. So I will be starting with values to the left of x equals to -2. We're in step 7. So if I let x equals to -3 and evaluate h of x at -3, I will have h of -3 equals to -3, -4 over 2 minus 3. And that should give me -7 over -1, which is a +7. I want to add the point I found in my data to my data, and I will have -3, 7. If I let now x equals to -4 and evaluate h at -4, I will have -4, -4, 2 minus 4. This will give me -8 over -2, which is +4. Adding this point to my data, I will have -4 and +4. Evaluating x at -5 in h of x, I will have h of -5, and that will be -5, -4, 2 minus 5. This will give me -9 over -3, which is +3. So the third point I found to the left of x equals to -2 is the point -5, +3. Now I would like to evaluate a couple of points to the right of x equals to -2. So if I choose x equals to -1 and evaluate h at -1, I will have -1, -4 over 2 minus 1. This will be a -5. I will add this point to my data, -1, -5. I will not consider x equals to 0 because I already know that it will be the y-intercept. I already evaluated it earlier. I want to choose x equals to 1. And h of 1 is going to be 1 minus 4 over 2 plus 1, which is -3 over 3, and that's a -1. I want to add this point to my data, 1, -1. Now I have sufficient points to graph my masterpiece. Finally, we will use the data we collected to graph our masterpiece. I already graphed the x and y coordinate plane. Also, the vertical and horizontal asymptotes at y equals to 1 and x equals to -2. I will plot the points, connect the points, and graph h of x. Starting with the x-intercept at 4, 0, I will plot the point right here, 4, 0. The y-intercept is a point 0, -2, and 0, -2 is here. The point -3, 7, -3, +7 is right there. -4, 4 is somewhere here. The point -5, 3 right here. The point -1, -5 is right here. And the point 1, -1. I know on the interval -2, infinity on the right side, my original function is concave down. Also, I know that h of x is always increasing. So concave down on here, I'll have h of x on this interval looking something like this. Now in this, on the interval -infinity, -2 on the left side, I know that h of x is concave up, and it is increasing. So I'm assuming it's going to look something like this, going through the points I found. And this is the graph of h of x. I hope you found this helpful. See you next time.